Hello everybody. In the last session we had started our discussion about the DC motors. Principally the DC motors and the DC generators belong to the same class, with the structure of the machine or the structure of the equipment being similar in both the cases. The structure of a DC generator can be used even for a DC motor, only that the flow of power is reversed. In the case of the DC generator, the power flows from the mechanical side to the electrical side, and in the case of the DC motor, the flow of the power is from the electrical to the mechanical side. All the equations and the principles involved are exactly similar to the case of the DC generator. The DC motor's back EMF, which is equivalent to the Lorentz force in the case of the DC generator, the induced EMF in both the cases, that is the back EMF here and the generated EMF in the case of the generator, are having the same equations, that is P and phi z by 60 volts. The only difference being the flow of power. In the case of the DC motor, it flows from the electrical to the mechanical side, whereas it is the other way around in the case of the DC generator. So, in this session, we shall continue our discussion of the DC motor. First, let us review what we have learned till now about the DC motor. We have the DC motor, which is represented as a circle, and it has two brushes. So, the armature makes contact with the electrical world by means of these two brushes, and the armature winding resistance is represented as an equivalent resistance RA as shown here. There is a source which is applied, a source voltage which is applied, and we call that one as EA across the terminals of the motor, and the armature of the motor is connected to a shaft, and which may be coupled to a mechanical load. Now, this DC motor when it is rotating will generate a back EMF or a counter EMF EB, which we discussed in the last class. And on the mechanical side, we have two variables which we need to consider. That is, one is the torque, which is the potential variable, and the other is the omega in radians per second, which is the kinetic or the flow variable on the mechanical side. And the flow variable on the electrical side is IA. Now, EB into IA is the power which gets into the armature, power delivered to the armature, and that is going to deliver the rotational power to the mechanical side. Now, the torque here we saw that the torque here is given by P phi z IA by 2 pi. This we saw in the last session, and we know that the induced EMF is P n phi z by 60. So, we see here that the induced EMF is dependent on this speed of the rotation. The torque is dependent on Ia. If we rewrite this here, EB equals P. Now, if it had been omega in radians per second, I have to convert that into RPM. So, omega, which is in radians per second, to convert it into RPM, 60 by 2 pi, where this is in rads per second. Now, this whole thing is in RPM, into phi into Z, total number of conductors in the armature. Phi is the flux per pole, P is the number of pole pairs, divided by 60, which gives you P omega phi Z by 2 pi, and torque is also given by P phi Z Ia by 2 pi. Now, let us have a constant K, which is defined as P Z by 2 pi. This constant K is number of pole pairs, total number of conductors, and 2 pi, which is a constant, and therefore it is a constant for a machine. Constant for a machine. So, therefore, torque is equal to K phi Ia, and EB is equal to K phi omega. Now, these two are the important equations in modeling the motor and also in determining the flow of the power and relations between the two sets of variables, the potential variable on the electrical side to the potential variable and the flow variable on the mechanical side, and vice versa. So, we now have a motor with brushes as shown here, and the mechanical port in the form of the shaft, and the electrical port in the form of these black wires being taken out from the brushes. Now, EB back EMF, which is induced here, is K phi omega. Torque okay, sorry, I will use the is given by generated torque is given by K phi Ia, isn't it? That's what we just now saw in the previous discussion. Now, what is Ia? Ia is the current that is flowing into the armature, or the armature current. And what is omega here? Omega is the speed in radians per second, and where K is equal to Pz by 2 pi. Now, you see that we have EB and IA on one direction, on one side, the electrical side, and you have generated torque and omega on the mechanical side. Now, EB is linked, the back EMF EB is linked with the speed of rotation on the mechanical side, angular speed of rotation in radians per second, that is omega, and IA is linked with the generated torque as shown by the equations here, and the linking variable is K phi. K phi is same for both the cases. So, therefore, this is a gyrator. We have already said that motor generators are gyrators, but this equations here emphasize our point that it is a gyrator and not a transformer. Now, looking at these equations here, the torque, generated torque is proportional to two quantities phi and IA, the armature current, phi the flux, the excitation in the machine. So, if we vary IA, the armature current, the generator torque is going to change, and for the given load, if the generator torque changes, the speed is also going to change. So, one could control the speed by changing IA, or one could also control the speed by changing the generated torque by changing this excitation or controlling the excitation. So, the generated torque which in turn is going to affect the speed of rotation, is affected by two variables, main variables, which is the field or excitation phi, and the other variable is armature current IA. So, by controlling the armature current IA or by controlling the field or the excitation phi or both, one can change or control the generated torque, and for a given load that is going to change the speed. This means that the speed of the DC motor can be controlled by changing these two parameters, by controlling these two parameters to achieve speed control. So, let us get back to the equivalent circuit and see how we go about achieving speed control. So, first let us do the control from the armature side. Armature side speed control. So, we have the motor, we have the brushes here, and brushes are connected to the terminals of the motor. They are brought out to the terminals of the motor, and we have a resistance RA, which is the equivalent resistance that we apply to the motor. Now, to this motor we are applying a source EA, and this motor mechanical shaft is connected to whatever load, mechanical load that one wants to connect, and this has the generated torque and omega, the two parameters, and on this side we are having EB, the back EMF, and IA, the armature current, which are the two corresponding variables, the potential and the kinetic variables, and this is the DC motor. Now, to control the speed, we need to change EB. Of course, the speed is going to affect the induced EMF EB, and we saw that TG was proportional to these two main things, the main parameters phi and IA. Let us first look at how we go about changing phi IA. Now, the armature current can be changed by either changing this or by changing IA itself by interposing a resistance in series with RA and making that variable, let us say RS or R series. So, therefore, when EA is varied, IA is equal to EA minus EB by RA. RS is still not put into the come into the picture. Now, if RS is put, then it is plus RS. So, let us say right now RS is equal to 0. So, if RS is equal to 0, we have this equation. Now, as EA is decreased, what is going to happen? EB has still not decreased. IA is going to reduce because EA minus EB is going to reduce, and as IA reduces, TG, the generated torque, is going to reduce because it is proportional to phi IA. All this while phi you are keeping constant, and because the generated torque has decreased, for the same load, omega, the rotational speed, also reduces, and because the rotational speed has reduced, this is going to affect EB, and EB is going to reduce because EB is proportional to omega. So, it will come and settle at the new equilibrium point or the new operating point. So, this is how the sequence of parameters that will get affected if you reduce EA. Now, if EA is not reduced, EA is just kept fixed, which means we introduce a series resistance RS. If a series resistance RS is introduced, here RS is finite, no longer 0. So, EA is fixed, EB is fixed for now. We are increasing RS. The moment RS is increased, IA is going to reduce. Reduction in IA is going to result in reduction in the torque, TG, generated torque, which is going to reduce the speed omega for the same load, and that is going to reduce the back EMF EB, and that will come and get settled in a new operating point. So, now EA minus EB is going to get distributed between RS and RA by their values, by the ratio of the values. So, in this way the speed can be controlled by either controlling the armature voltage or by controlling the armature current by way of a series resistance or rheostat connected in series with the armature. Now, between the two methods, if you see, if we introduce a series resistance, the whole IA current, the armature current is going to flow through the series resistance, and there is going to be a IA square RS drop. So, for a power which is EA into IA that is going to be taken from the source, and EB into IA that is going to be delivered to the armature, IA square RS and IA square RA gets lost as heat, out of which IA square RA is inevitable and unavoidable because RA is the armature winding resistance. So, what is avoidable is IA square RS, the series resistance that we have put here to achieve speed control. So, if IA is large for a very high loads, then there could be significant loss in the series resistance, and therefore, the efficiency of the motor will suffer, because the efficiency is basically P out by EAIA minus IA square RA minus IA square RS. So, this is going to reduce the efficiency of the plus I am just going to rewrite this, P out divided by EBIA, the power delivered to the armature, plus IA square RA plus IA square RS, and we see that this is going to reduce the efficiency of the motor. So, it is preferable to do armature voltage control rather than rheostat control. So, in the armature voltage control, one could have two machines connected back to back as shown here. Now, let us say this is one machine, this is the actual motor which is going to the mechanical load, and there is a RA here as shown in the circuit, and this is the terminals of the motor. So, this is the motor. Now, here we have the field coil also, which I am going to show here, and I will indicate that there is a field current IF which is flowing through the field coil to give a flux phi. So, phi is set up in the field. Now, this can be coming from some other source. So, there could be a resistance here and probably a battery connected here. So, this could be R field RF, and this is EF, let us say REF. We have been using E everywhere, so we will use EF. So, this is the field coil coming from a separate source. So, this is a separately excited motor. This is a separately excited motor, just like in the case of a generator, the separately excited generator case. Now, we need to apply an armature voltage EA that is capable of being varied, a DC voltage. So, to the terminals here, let us connect a generator which has its own RA, which comes from again another machine, another similar machine, but it is being operated in the generator mode. So, this is a DC generator, this is a DC motor. And the shaft of the generator is being driven by a prime mover. And this generator also has a field coil, of course, as explained before. There could be a resistance, there could be of course a battery, some other separate source. So, you have an RF and an IF which is going to generate phi, and this is an EF. So, this is going to excite the generator. This is also separately excited generator. So, the speed of this shaft or the torque supplied or the energy supplied through the mechanical domain, this could be moved by prime mover, could be a AC motor or some other prime mover like a IC engine, that is the internal combustion engine, or any of those things. This prime mover is going to supply the mechanical energy through the generator, generates the EG here across generator. Then after the drop, what you get here is E naught. E naught is the armature applied voltage to the motor. So, here you have the motor, here you have the generator. See. So, E naught and EA are same. Now, that for this generator the load is this motor. So, this EA is applied to the motor and this motor is going to deliver again energy back to the mechanical domain. So, if we control the speed of the prime mover, the generated voltage here, because this is again dependent on the speed here. If this is rotating at n RPM, what you are going to get here is EG, which is equal to P n phi z by 60. So, n here is going to affect EG. So, by changing n, EG changes, E naught changes, and therefore, EA changes, which is going to change the torque, generated torque here, which is phi IA, which is going to affect omega. So, the speed of this mechanical shaft of the motor side is controlled by controlling the speed of the mechanical shaft of the generator. This type of speed control system is called Ward-Leonard system. This is called the Ward-Leonard speed control system. This is for speed control. This is a very rugged method of and useful method of controlling the speed of the DC motor, especially high power systems. The other method that we said could affect the speed of the mechanical side, that is the omega, is by controlling the excitation of the flux or the field, because Tg is proportional to not only Ia but also to phi. So, if we are able to change phi, then we should be able to affect Tg and thereby the speed for a given load. Now, how do we change phi? Changing phi is not a difficult issue. You see that we have a circuit here which is generating the field or the excitation. So, there is a source EF and that EF is passed through RF and the current IF or the field current is flowing through the field coils. So, two possible ways of controlling IF. So, if we change IF, because phi is proportional to IF, so if we change IF, phi is going to change. So, IF can be changed either by adjusting this resistor or by changing this voltage value of this voltage source. Both these will change phi, which will lead to change in Tg, which will affect the speed of the motor. But the manner in which we are going to change phi is going to depend also on the way the motor is going to be excited, and the motor is excited in the following ways. Generally, we have three main categories for the motor for excitation: motor, field, excitation. So, first method called the shunt motor. So, the name shunt motor is got from the fact that its field is excitation by having the field coil connected in shunt or across the motor terminals. The series motor. The series motor is a motor wherein the field coil is connected in series with the armature winding, and thereby the armature current flows through the field. And third is the compound motor. So, in the case of the compound motor, as the name suggests, it is a mix of both. You have two sets of coils, the shunt coil and the series coil. The shunt coil is connected across the motor armature. The series coil is connected in series with the motor armature. So, that is the compound motor, and these are the three main types of motor that you would come across, general categories. However, there are few other types of motor, like the excitation could be by permanent magnets. Then we have the permanent magnet DC motor, or the excitation could be from a separate source, like in a separately excited DC motor, and so on. Now, let us look at the characteristics of these three types of motors to get a better idea about these. So, in the case of the shunt motor, we make the following connection. So, we have the DC motor along with the brushes as shown. Now, let me put the armature like this. This is RA, the armature resistance is connected like that, and this is connected to the source EA. So, the source EA is connected like this as shown. There is going to be a armature current IA which flows through, and this would result in a back EMF EB across the brushes. Now, we have the field. Now, the field coil can be shown in the following manner. We have the field coil which is shown like that. Now, this field coil goes through a field resistance and gets connected to the terminals as shown. This is RF, and of course, EB gets induced across these terminals, or we will put EB through here. So, that gives a much better picture. And we have the mechanical shaft connected as usual to a mechanical load. There is a field current IF which flows through the field coil to produce flux phi in the machine, and the torque Tg which is generated is proportional to phi and Ia. Now, you see this field coil, what is shown in green is the field coil which is connected across the terminals of the motor, and what is applied is the same voltage whatever is applied to the armature. The EA, what is applied to the armature, is also applied to the field, and this is called the shunt connection. This is a shunt field motor. So, the field current generally is very small compared to IA. IF is very small compared to IA, and therefore, the field coil can be rated for a lower current, and therefore, the gauge of the, that is the thickness of the field wire, will be very small in general compared to the armature winding thickness. By varying RF, that is by making RF variable, the field current can be controlled, and therefore, IF can be controlled, or the flux can be controlled as a consequence, and therefore, the Tg can be controlled. So, in the case of, let us say, a constant, constant field motor, let us select this, copy, paste. So, in the case of a constant field application, phi is a constant, then Tg becomes proportional to only Ia. So, therefore, as a result, as Tg is proportional to only Ia, the torque varies linearly with the load. So, let us have a graph of torque versus Ia, and let us say torque. So, the torque would vary linearly with the load. So, this is Tg versus Ia. This will give you the load characteristic. Now, if we look at the shunt motor curve with respect to the torque with respect to the speed, what happens? Now, Tg into omega will be the power. Tg into omega is the power. Now, let us say we want to keep the power constant. So, when the power is constant, then Tg is inversely proportional to omega. That is, Tg is proportional to 1 by omega. So, with speed, so if we have speed as one of the axes, then T with respect to speed is going to decrease like that. T is inversely proportional to, so T versus omega. So, as omega increases, torque is decreasing. So, this is Tg generated, and let us say this is Tg which is load dependent, the Tg value which is load dependent, or the torque value which is load dependent, and therefore, we will say this is the load line, this is the load, this is the generated torque by virtue of its rotation, and therefore, this is the operating point. And because the power is constant, meaning we are at, let us say, the maximum power P max, let it be constant at, let us say, P max, then this would indicate maximum or rated load, this particular operating point. So, the torque at rated load and rated speed or the nominal speed. So, that would be your Ia rated, omega rated in radians per second. On the other hand, what if we are not keeping power constant? So, let me draw a graph with respect to the speed omega in radians per second. This is the torque, because Newton meter. Now, let us say I keep on increasing the voltage. As the voltage is being increased, the voltage will keep on increasing as shown, let us say, up to a certain point. So, this is the, beyond that the voltage can't increase, because we would have reached the rated value of the voltage for the machine, EA rated. So, this is the EA curve. This is EA with respect to speed. Now, let us for the moment take RA equal to 0. So, which means EA is same as E naught. So, this is actually the back EMF also, because we are saying RA, this is the back EMF EB, because RA is equal to 0. Beyond a particular speed, the back EMF has reached the same value as the rated voltage, and we can't apply a voltage more than the rated voltage, in other otherwise the machine will saturate. So, it has to get clamped at this beyond a particular value of the speed. Now, what is happening to the power? The power that is delivered to the armature is EB into IA, or EA into IA, because RA is equal to 0. So, the power curve is EB into IA, which is the power which is put into the armature. Now, as EB is 0, the power here is going to 0, and that is going to increase. So, let us say the power curve increases in some fashion up to this point. So, at this point, this is the power curve P in watts. Now, at this point, torque rated has been reached, omega, that is speed rated or the nominal has been reached, whatever is given on the nameplate, and IA is also rated. Beyond, let us say we want to still increase the speed. What happens? EA cannot increase any further, speed only can change. And how can you increase the speed by keeping EA constant? By decreasing flux only, because TG is proportional to flux into IA. We are not going to change anything on the armature side, because armature voltage is now reached its maximum constant. So, only other parameter to control is phi, and phi you can't increase more, because already the voltage is the maximum. Any increase in the voltage will saturate. So, therefore, you have to only decrease the flux. So, we decrease the flux. So, which means TG starts reducing. So, you can still go beyond the rated speed by reducing the torque. So, the torque will start reducing in this zone, and the maximum that can be available is TG is P maximum by omega. So, if we say P maximum is constant for the machine, then TG is inversely proportional to omega. So, if I am having a TG curve, so let us say this is TG max. So, that will start going proportional to 1 by omega as omega is increasing. But in this region, you could achieve a constant torque up to maximum by changing these two. So, there is possibility of obtaining a constant torque here, because the speed is less than the rated, and as the speed is less than the rated, IA can take a lesser value, and therefore, for any load one could achieve a constant operating point below the rated, but beyond the rated there is upper limit for the torque, which will take have a proportionality of 1 by omega. So, this would be the achievable maximum torque curve, the green line as I am showing here, with respect to omega. Now in the case of the series motor, what happens? So, in the case of the series motor, we have, let us say, the same machine. We have the brush and I have the armature resistance Ra as shown here across these terminals. This is the brush and this is the DC motor. This is Ra and this is brought out to the terminals here. And there is a back EMF Eb across the brushes. There is also an applied voltage Ea across the armature, and there is a current Ia through the armature windings. There is now a field winding. Now, this field winding is not going to be connected directly across the terminals, but it is going to be brought out here and connected in series with the armature. So, what we do, we make a cut here and then connect it like that. So, which means the Ia flows through the field coil to produce also the flux and also the load. And then what happens to the torque at the mechanical side? The torque on the mechanical side that is generated, we know is proportional to the flux into Ia, but the flux is proportional to the field current, but the field current is same as Ia. So, flux is proportional to Ia and therefore, Tg is proportional to Ia square in the series motor. So, in the case of the series motor, we have the flux which is proportional to Ia and therefore, the generated torque Tg is proportional to Ia square. So, therefore, if we look at the load torque characteristics with respect to Ia, we see that this starts having a hyperbolic Tg versus Ia in the case of series motor. Now, let us see Eb. Now, Eb is also proportional to phi Ia, is proportional to phi omega phi into omega, or Eb is proportional to Ia into omega, because the flux is also proportional to. Now, Eb into Ia is the power. Eb into Ia is the power, and therefore, the power is proportional to Ia square omega. And let us say we want to keep the power constant. then then IA square omega will be a constant. Of course, IA square is Tg, proportionality is there in the fact that, and it is proportional to, the torque will be proportional to 1 by root of omega. In the case of Tg is proportional to IA square and 1 by omega, but Tg is already IA square, and therefore, the armature current or the load current will be proportional to 1 by root of omega. In the case of the series motor, whereas in the case of shunt motor, IA was proportional to 1 by omega. Now, if we take this equation EB, which is equal to P n phi z by 60, or P z by 2 pi into phi omega, where this is in RPM, this is in radians per second, and this is K which we had defined. So, which is equal to K phi omega. Now, let us say in the case of the shunt motor. So, in the case of the shunt motor, let us say this is given by the applied voltage, which is therefore, it is connected across the terminals, and therefore, this is not 0, phi is not 0, and EB is proportional to omega. When omega is equal to 0, the induced EMF is 0. If the flux is brought to 0, what happens? Now, EB is, let us say, approximately equal to EA, and let us say for the moment for the discussion RA is equal to 0, then EB equals EA, which is proportional to phi into omega. Now, this if we keep it constant, it is a constant DC source which is applied externally. If you reduce the flux, the field is going to increase, so that the product is a constant. So, if this is suddenly made 0, let us the shunt field winding coil is made suddenly 0, then under no load conditions, the speed here can increase phenomenally high, and it may break away and damage the machine. But in the case of the series motor, when the field coil is broken, IA is also 0. Because IA is 0, because this is proportional to IA, and omega is also proportional to, because we saw that omega is also a function of IA. IA is proportional to 1 by root omega, or omega is proportional to IA square. So, when IA is made 0, both the speed also will become 0 because that is a function of the speed, and the motor does not run away. Whereas, in the case of the shunt motor, there is a possibility of running away. We will stop here and continue our discussion in the next session.